Hi team, we're looking at section 3.2, solving quadratic equations. And remember, a quadratic equation has the highest variable exponent of 2. Nice little polynomial there. The 5 ways are graphing, and this way can be messy if you've got a lot of graphing to do and they're not exact values. The second way is the square root method, but this only works if you only have a squared value, but you don't have the x term. In other words, it's just x squared and there's no other variable. We also have completing the square. This is, can be messy, but always works. We have factoring method, but this is only if factorable. And last but not least, we have the quadratic formula. This guy always works. So we're going to go over those 5 different methods today. So first of all, when we're graphing, when we're solving for a quadratic set equal to 0, remember that's like saying the f of x is 0, that output value. So we're finding the zeros or the x-intercepts. So again, when we're trying to solve a quadratic set equal to 0, it depends on how many x-intercepts we have as to how many solutions we can have. So I know we looked at this earlier. If we've got one like this, it is possible to have 2 solutions to the equation because we have 2 x-intercepts. If the parabola only touches the x-axis and bounces off, then it's possible to have only 1 solution. And if the parabola opens up away from the axis and doesn't cross the axis at all, then we have no solution. So in this next example, we're going to use the graphing method by graphing this example on our calculator and finding the zeros. So if we plug in that equation, we would get x squared minus x minus 6. And then if we hit graph, ta-da, we get this guy right here. So again, we're not looking for the vertex this time. We're looking for where the function equals 0. So it looks like if it hits straight on, it looks like we're at -2 and 3. But if you're unsure, we can always go to calculate. So second function trace, we want to calculate the zeros, and then we follow the instructions here on the left. If we try to find this left 0, we're going to move the cursor left bound, enter, to the right of that 0, enter, ask it to guess, and it is in fact at -2. And then we can do the same thing to this other side, but it does in fact look like it's at 3. If you're not sure, you can also plug in -2 into that original equation, see if you do in fact get 0. And plug in 3 into the original equation, see if you do in fact get 0. And if so, those are your 2 solutions. So from that graph, we got 2 solutions of -2 and 3. Now let's take a look at the square root method. And remember, this method only works if it has an x squared term, but not an x term. With this first example, we can use the square root method. We would subtract 5 from both sides, get 3x squared equals 18, divide both sides by 3, and we get x squared equals 6. To undo an x squared, its opposite operation is a square root. We can take the square root of the left side, but when we take the square root of the right, we have to consider both the positive and negative square root of 6. So x would be a negative square root of 6 and a positive square root of 6. For problem number 2, I know we see an x to the power of 1, but it's part of a binomial that's being squared. So let's get the part that's being squared by itself. So we divide both sides by 4, and we're left with the quantity x minus 5 squared equals 8. To undo that square, we take the square root of both sides. Don't forget the plus or minus with the square root of the 8. So the left side reduces to x minus 5. We got rid of that square. But let's recall how to reduce that square root of 8. Remember, 8 breaks down into 2 times 4. 4 breaks down into 2 times 2. Since it's a square root, we are looking for numbers that are being squared. I have a 2 times a 2 there, so that 2 can come out. That 2 does not have a pair, so he has to stay in. Since this guy is 2 squared, so we get 2 square root of 2. And we still need to get the x by itself. So we add 5 to both sides, but we cannot combine 5 with a square root. So we just write them side by side, 5 plus or minus 2 square root of 2. Now let's review completing the square. But first, let's focus on what it means to square a binomial. So if we had x plus 3 quantity squared, and we were to expand it, x plus 3 times x plus 3, and then distribute, we would get x squared plus 3x plus 3x plus 9. Notice how these two show up identical. The outside and the inside will give you the exact same binomial. We could write that as 2 times a 3x plus 9. So that guy in the middle gets doubled. So we get x squared plus 6x plus 9. The relationship here is this last number happens to be the 3 squared, and this middle number happens to be the 3 times 2. So what we're going to do is we're going to have the original trinomial, and we're going to work it backwards in order to factor it into a binomial squared. So here's an example of completing a square. The first thing we want to do is divide everybody by the coefficient. So everybody's going to get divided by 2 because you want your leading coefficient to be 1 no matter what. Even if it gives you fractions, even if it doesn't go in evenly with everybody, you want to divide everybody to get a leading coefficient of 1. So step 1, divide by the leading coefficient. Then we're going to keep all the terms that have variables on one side. I want you to put plus blank here. And we're going to move that constant of -3 and make it a +3 to the other side and put a plus equals there. So step 2, move variable terms to one side and constant to the other. Now this next step is kind of the important piece. So we got to remember that the middle number is doubled the number we're looking for. So if our middle number here is 6, we're going to take half of that coefficient of that x. So a half times 6 gives us 3. And then we're going to square that number and add it to both sides. So we're going to add a 9 here, but to keep it equal, we're going to add a 9 to the other side. If we have completed the square correctly, that trinomial will automatically factor into x plus 3 squared, either half the 6 or the square root of the 9. That's where we get that 3. And we can solve the right-hand side. That gives us a 12. And now we can use the square root property to finish solving. Square root of the left plus or minus the square root of the right. This leaves us with an x plus 3 equals plus or minus. Again, if we looked at that 12, we'll do it here on the left. 12 breaks down into 2 times 6. 6 is 2 times 3. I have a pair of 2s, so that means a 2 can come out. This 3 is not part of a pair, so he has to stay in. So we get 2 square root of 3. And then we subtract 3 from both sides, and we get x equals a -3 plus or minus 2 square root of 3. Our next method is the factoring method, and that's based on this concept here. If you have 2 variables, a times b equals 0, what must either a or b equal? Well, either A equals 0 or B equals 0. So that's kind of the product rule of 0. When you multiply and you get 0, somebody has to be 0. So when you are factoring, you are putting things into factors that multiply to equal a number. So to solve by factoring, we have to have it set equal to 0. And if it's been a while since you factored, I put in your guys' modules a whole bunch of reminder videos on how to factor with different methods. GCF, grouping, trinomials, using a couple of different methods. I'm going to use the bottoms up method here, but you guys can use whichever method you prefer. So we first notice on the left that there is a GCF. Everybody here can be divided by 3 evenly. We're going to take out that 3. That leaves us with a 3x squared plus 5x minus 2 equals 0. And now to factor this trinomial, we can multiply the first and the last term. I like to do that out to the side. So we'd have 3 times the negative 2, which would give us a negative 6. And then we're going to find factors of negative 6 that add to the 5. So we would have negative 1 times 6, negative 2 times 3. Well, these two, if I were to add them, negative 1 plus 6 does in fact give me the 5. Some of you may be used to using, some people call it the diamond method or the big X, where you say, okay, it has to multiply to give me a negative 6, but add to give me a positive 5. And then you find those two numbers that work, like negative 1 and 6. That's the exact same thing that we're doing here. I just list all the factors because inevitably the 2 factors I need are going to be the 2 factors I don't think of. So that's why I make the list. But these 2 here, these are the same. Okay, same idea. With the bottoms up method, we would start with just the minus 1 and with the x plus 6. This 3 out here is still on that outside. But if you notice, we have this 3 here. Well, if I were to distribute x times x doesn't give us 3. So what we do is we take that leading coefficient and we put him under here. Now, again, that's this 3. If it does not reduce, or if it reduces, but you're left with a number on the bottom, then he moves up with the x. So we still have the 3 on the outside, but then we get a 3x minus 1. This is why this is called the bottoms up method. But in the second binomial, 6 divided by 3 actually goes evenly, and we have just a positive 2. Dum, dum, dum. And so that is our expression on the left factored. But remember, all of these equal 0. And again, you can always go back to those factoring review videos that I've posted in your modules. So that means either the 3x minus 1 equals 0 or the x plus 2 equals 0. This 3 here will not be set equal to 0 because it doesn't have a variable in it. 3 by itself will never equal 0. So only the factors with an x. So on the left-hand side, if we add 1 to both sides, we get 3x equals 1. Divide both sides by 3, we get x equals 1/3. And on the right, subtract 2 from both sides, we get x equals
-2.
So those are our 2 solutions by factoring. Our last method is called the quadratic formula, and this guy always works. Basically, if we were to take the quadratic equation, ax squared plus bx, guys, I apologize. Some of them have equal signs instead of plus signs. Ax squared plus bx plus c equals 0. And if we were to complete the square, use all of those steps on this generic form, we would get the quadratic formula, which says x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So notice that that is one huge fraction, everything over 2a. So the A, the B, and the C are the numerical coefficients of the three terms on the left. So be sure that these three terms on the left are in descending powers. Your squared term first, then your x term, then your constant. Also, be sure it's set equal to 0. So let's use the quadratic formula on this example, where 3 is our A, 2 is our B, -4 is our C. So x equals the opposite of 2 plus or minus the square root of our B squared, so 2 squared, minus 4 times our A, which is 3, times our C, which is a -4, all divided by 2 times our A, which is 3. So we get a -2 plus or minus the square root of 4 plus 48, I believe, divided by 6. So we get a -2 plus or minus the square root of 52 divided by 6. We want to see if that 52, that square root of 52 can be reduced. So we take 52, that's 2 times 26, which is 2 times 13. So again, we have a 2 squared, and the 13 does not have a pair, so he stays in. So we can rewrite this as -2 plus or minus 2 square root of 13 divided by 6. It's at this point that we can reduce, but everybody has to get divided by the same value. In other words, we have a 2 plus or minus a 2 over a 6. All three of those outside values can be divided by 2. So divide this guy by 2, divide this guy by 2, divide this guy by 2. We can't divide the square root of 13. It's a radical. So that's going to give us a -1 plus or minus. You can write that 1 in front of the square root of 13, but you don't have to, all over 3. So that would be our final answer. There is something called the discriminant, and this is the portion underneath the radical, the b squared minus 4ac, and it helps us to determine the number of solutions. Let's write the entire thing over 2a, and let's highlight this. This is the discriminant. So if we have two solutions, what's underneath that square root is going to be positive, because remember, we have that plus or minus the square root of a positive number. So that's going to give us two values. Just like this problem up here, that plus or minus represents two numbers, -1 plus the square root of 13 over 3, and -1 minus the square root of 13 over 3. So if that number's inside positive, then we have the two solutions. So that's one possibility. The second possibility, if there's one solution, is if that discriminant equals 0. The square root of 0 is 0. So if you add a 0 and subtract a 0, you still get the same number. It doesn't change. So you'll only get the one number. No real solution is if that discriminant is a negative number. Remember, we cannot take square roots of negative numbers in the real number system. And we're not going to be going over complex numbers. So we're set with just the square root of negatives being not a real number. Our very last problem is going to be a modeling problem involving quadratics. So we've got a total revenue function for a home theater is given by R equals 266x. And the total cost function is given by C equals 2000 plus 46x plus 2x squared, where R and C are both measured in dollars and X is the number of units sold. Well, first of all, they want to know the profit function. Remember, the profit function is our revenue minus our cost. So for part A, to find the profit function in terms of X, we're going to take our revenue function and subtract our entire cost function. So do not forget to put in your parentheses so you can distribute that negative, and then combine like terms and write it in descending powers. So we figured out what the profit function is. Now in part B, they want to know how many units must we sell in order to break even. Well, remember, when we break even, there is no profit. There is no loss. Our profit is zero. Our revenue equals our cost. So for part B, we would set it equal to 0. And it doesn't matter to me which method you use to solve it. Be sure you do know how to work it by hand, not just using your graphing calculator. That gives you a good visual, but try the factoring method, or like I said, the quadratic formula always works. I think this is factorable. I could be wrong, but let's try it. I'm going to factor out a GCF of a -2. I want factors of 1,000 that add to a -110. Well, if it adds to a positive, I'm sorry, if it multiplies to a positive but adds to a negative, they're probably both going to be negative. To save a little bit of time, it's going to be a -100 times a -10. And again, if we added those together, that would give us a -110. So we'd get x minus 100 and x minus 10. We set both of those equal to 0. We have 2 break-even points where we no longer make a profit or loss is at 10 and 100. Well, that may sound confusing to you because we have 2 break-even points. So how do we know which one we need to sell more than or less than? Well, remember, we have 2 functions. One is linear and one is a cost function. And we want to know where they equal each other. If we were to graph those 2 functions, one is an increasing linear function, that's your revenue, and the other one is a cost function like this. So this point here is at x equals 10, and this point here is at x equals 100. So remember, you want your revenue to be higher than your cost. So it's here in between 10 and 100 that you're going to make a profit. That's why both of these break-even points are important, because you need to know whether or not you need to be on the outside of those break-even points or the inside in order to make a profit, where your revenue is higher than your cost. All right. That is it for section 3.2. If you have any questions, don't hesitate to contact me or your instructor. And again, if you need some review on factoring, I've posted some in my modules. Otherwise, you can look up factoring on YouTube, Khan Academy, Algebra Help for Humans. There's a lot of different videos out there where you can find some factoring help, or come and see us. All right. Bye, guys.